All right, so trusted execution is dead and we've killed it is most likely what Friedrich Nietzsche, the German philosopher, would have said if he was still alive and would be working on cryptography-based, trustless, confidential computing. So today I want to introduce you to the current state of this kind of confidential computing and share how Arcium's vision works on confidential computing. So, my name is Yannik Schrade. I'm the CEO and co-founder at Arcium. We are the first of its kind decentralized and trustless confidential computing network. 2.5 years ago, we founded our startup in Switzerland, have since closed 2 funding rounds, and have grown into a rapidly expanding, globally distributed team of researchers and engineers. Let's first start by investigating why trusted execution is dead, or rather look at the inherent flaws trusted execution brings. So the first problem many of us encounter is performance overheads when running confidential computations in trusted environments. And trusted environments like Intel SGX bring security promises, but those promises come at the cost of performance. So entering and leaving trusted execution environments, encrypting and decrypting data, and switching between secure and non-secure contexts require memory, require cost, and memory allocation in general is quite limited. On top of that, developing secure software inside of TEs is also not straightforward. So often, to be able to develop efficient implementations, you need to have a deeper understanding of cryptography and of secure coding practices, which introduces development cost overhead and not abiding to those safe standards and making even the smallest kinds of mistakes by not respecting the boundaries of enclaves can lead to severe security breaches. And so developers need to spend a lot of time in testing and validation, and using third-party services and frameworks often results in a large dependency stack and trust in additional third parties. And then deploying TEs is also not the cheapest way of doing confidential compute. So you either run your own hardware, which means you have some upfront investment of getting that hardware, and you have to provide secure storage locations and personnel to maintain those devices. If you utilize cloud service providers, you introduce trusted entities and pay premium prices. And all of those issues are not that bad. They can be managed. The most important issue really is that trusted execution comes with a flawed trust model. So those issues will go away with scale and maturity of technology, but the trust model is fundamentally misaligned, and I want to go into the details of different attack vectors that highlight why this trust model is flawed. And so on the first kind of attack we want to look at is side channel attacks and hardware vulnerabilities. So I just want to run through a few examples to highlight to you the severity. So if you look at the foreshadow attack, that attack exploited speculative execution vulnerabilities in Intel processors and allowed to breach the isolation of SGX enclaves. The SmashX attack utilized re-entrancy bugs in SGX SDKs, allowing to exploit sensitive data. The Plundervault attack utilized manipulation of voltage and frequency of the CPUs in order to be able to access data beyond the boundaries of enclaves. And SGX utilized cache side channel vulnerabilities to extract information. And those are only a few examples from the recent years, and even last year we've seen multiple of those CVEs, and that's essentially the track record on this front. And then we also have firmware, microcode, and SDK bugs that in the example of Spectre or Meltdown can result in extensive mitigation measures, having to upgrade the firmware and microcode across the entire deployed hardware. And zombie load is another example where using microarchitectural data sampling, data access across enclave boundaries was possible. And so those are those hard exploits we've seen in the past, and it's only a very small sample of the total set of exploits. The biggest problem, however, trust-wise, really are supply chain attacks. And supply chain attacks can allow attackers to target individual parts of the entire supply chain. And this supply chain involves a lot of trusted actors that ranges from hardware manufacturing over software distribution, over attestation, signing, and certificate services. And so attackers mainly only need to focus in on one of those points and are able to hijack the processes, are able to introduce backdoors, and since those systems are proprietary and non-verifiable, there's essentially no way of knowing. Relying on those systems, on proprietary systems and supply chains, as we've seen with the Shadow Hammer attack with ASUS in 2019, which resulted in attackers being able to utilize legitimate ASUS software signing keys in order to distribute malware across over 1 million devices, really highlights that if something like this happens in the confidential computing space, if something like this happens with trusted execution environments, and we more heavily depend on this technology, we're simply waiting for a disaster to happen. And so what can we do about this? We need to essentially eliminate those single points of failure. This system of many trusted actors is a system of many points of failure, and all it could require could be a simple social engineering attack in order to hijack one of those points. And so what I now want to look at with you is different cryptographic approaches that can help or be an alternative to this. And so the first are zero-knowledge proofs. Zero-knowledge proofs are a cryptographic protocol that allows one party, the prover, to prove to another party, the verifier, the truth of some statement without having to reveal the statement. And so this statement can be a computation over sensitive data. They can prove ownership and execution of some computation using that sensitive data without having to reveal that data. That means that zero-knowledge proofs have some very powerful properties: completeness, soundness, and zero-knowledge. Completeness means only valid proofs can convince a verifier. Soundness means invalid proofs can't convince a verifier. And zero-knowledge means that in this entire process, no data is being transmitted. This technology is already heavily being used in the blockchain space for full mathematical privacy. The issue with zero-knowledge proofs, however, is that what we are striving for is an autonomous execution environment. We cannot utilize zero-knowledge proofs for confidential compute, since we need one party to have plain text data access and generate those zero-knowledge proofs. And so we cannot have autonomous execution. And another technology we could utilize would be fully homomorphic encryption, which allows to perform computations over encrypted data. So we have an encrypted representation of data and run operations over that encrypted representation, which again yields an encrypted representation. So the data does not have to be decrypted in the process. The issue with fully homomorphic encryption in practice is a very significant performance overhead, many orders of magnitude above normal execution over unencrypted data, which renders it impractical. It also has other weaknesses like noise accumulation, so repeated operations over the encrypted state, aggregating noise, which needs to be removed by decrypting and re-encrypting the data, introducing trust to the system again. Verifiability is also not as easy and natively supported as with other kinds of protocols. And selective disclosure by default is also not given. So if we have an encrypted representation, we cannot reveal information outside of that encrypted data just with FHE, because we can just perform those homomorphic operations over the encrypted state. And so a more practical and scalable technology are secure multi-party computations, MPC, and what they allow is for collaborative computations over private inputs. That means that multiple parties can hold private data and run a shared public function over that private data without having to exchange the data to one another directly. The core principle we are working with multi-party computations is secret sharing. And secret sharing circles around this idea of parties having secrets and dividing those secrets, blinding those secrets, essentially encrypting them and exchanging them with one another. And then at some point, pooling all of those secrets back together, those shares together, would yield the original secret. But in this intermediary process, the parties holding only individual shares learn nothing about the secret. They only hold those shares. And with multi-party computations, we can have computations be executed over those shares and hence maintain privacy for the input values. And so multi-party computations are based on the trust model, into which I will go into a second, can be viewed from a higher level as blind computations by multiple parties. They're able to run this shared function, gain shared insights over isolated data. In order for us to leverage this technology for confidential compute, there's essentially two applications with multi-party computations. One, the most native application, is to have a collaborative setting, to have multiple parties with isolated data silos that want to run a function. They want to perform federated learning. They want to find the intersection between multiple data sets without having to exchange this data. That's the most native use case. However, what we're looking for is a secure environment where we can deploy encrypted data without having to actively be part of that computation, right? Just like deploying into a cloud. And so what we utilize for this is threshold encryption. And threshold encryption essentially is an encryption scheme where a decryption key does not exist at one place, but instead key shares to that key exist, distributed again amongst multiple parties. And then a threshold, or the total number of those shares, need to be put together in order to be able to decrypt data. And if we combine this concept of distributed key shares amongst multiple parties with a multi-party computation, we can utilize those key shares as secret inputs, essentially, that are being input into the multi-party computation. And inside of this blind computation, the data can be decrypted and can be accessed and computations can be executed without the data ever existing in plain text, without any of those parties ever having individual access to the data. Only the entirety of the players, the threshold, would be able to have access to that data. And so trust-wise, what we're looking at is two different models, the honest majority and the dishonest majority model. The honest majority model requires that more than half of participants in such a computation behave honestly, and the dishonest majority trust assumption requires that in the best case, only a single participant has to be honest. So this adversarial model allows for the best security guarantees you can have in a trust involving distributed setting. And that's why we want to target this dishonest majority trust assumption, which by default comes, however, with performance overhead. Because as you can imagine, if a protocol allows for having only one honest actor that can't be controlled by one single entity controlling all others, more cryptographic safeguards are required than a system where you can trust-wise assume that more than half is honest. And so what's important is that in recent years we've seen significant performance increases in multi-party computation protocols, so-called protocols in the pre-processing model from the speeds protocol family. And what it means is that computations are split into two phases, an offline pre-processing phase and an online phase. And the online phase is where the actual computation takes place. So the computation and the concrete inputs are being used to yield an output, and data from the pre-processing phase is required for that online phase. However, this data produced in a pre-processing phase can be independent of the concrete inputs and even independent of the concrete algorithm that is being executed in the online phase. And so by splitting those two phases, a lot of work can be performed up front. And so once computations should be executed, it's possible to use this essentially correlated randomness that is being generated in the pre-processing phase to rapidly execute those computations. And those performance increases essentially have made those protocols now feasible for real-world and real-time applications. And that's what we are doing at Arcium, utilizing those protocols. So in our case, what Arcium is a global, permissionless, and distributed network. We use the BDOSA MPC protocol, which is a MPC protocol in the pre-processing model, as I just described, with dishonest majority trust assumption. And trust-wise, this is great because it leaves us with this trust assumption that for a computation, we only need, in a large distributed network, one single participant that is not collaborating with all of the others to undermine confidentiality. But the issue in practice would be, if you just were to use those theoretical papers, that having this low trust assumption on the flip side means that also one dishonest actor could stop the execution of the entire computation because they provide invalid data, they provide invalid shares to their key share, or they simply not collaborate in the computation process itself. And that's a practical problem we had to overcome because we don't want any trusted systems in our architecture. We want it to be decentralized and no trust involved. And if there's no trust involved, you still need guaranteed execution for your computations. And we were able to achieve that by extending BDOSA essentially with cheater identification, which allows us to cryptographically identify misbehavior in the computation. And the additional work that we need to perform to be able to have this cheater identification occur all happens in the pre-processing phase. So it doesn't affect performance at all, while allowing us to identify that a specific party has misbehaved in the computation. Now, what do we do when we have such a proof that someone misbehaved? We utilize a disincentivization mechanism where each node in this network first needs to stake collateral, stating essentially joining with a contract saying, if I misbehave, please take my money away. And that's what we are doing. So we are using a distributed ledger, existing distributed ledgers, blockchains for that, where those nodes have this negative disincentivization mechanism, where if cheating occurs on this distributed ledger, that is being cryptographically verified and their collateral is taken away. And at the same time, they're being positively incentivized. by those ledgers being those trustless and transparent pipelines for payments, and forming those open markets where you have essentially a peer-to-peer market between computational customer and computational clusters that offer those confidential compute services. And at the same time, we have a transparent public registry of all participants in this network. We have a full track record of all participants. And so you have this unforgeable track record where you can see all past misbehaviors that have been identified. And we use all of that in what we call MPC, execution environments, MXEs. And so those are virtual encrypted environments that the computational customer can create. And each environment has one or multiple computation clusters associated with them. And those computation clusters then run so-called distributed key generation protocols, where those key shares that are then the private sensitive inputs into the multi-party computation are being generated, and a public encryption key is also being generated at the same time. So that's a multi-party computation in itself. And then this MXE has the dishonest majority trust assumption again. So the user, at the end of the day, can specify what their trust assumptions should be. They can create a cluster with 100 nodes. They can create a cluster with 10 nodes. And all they need is one honest participant in those clusters. They can create encrypted data objects inside of those MXEs, and then they can essentially have arbitrary computation support. So any LLVM compilable language is supported, and you can have arbitrary operations happen over your arbitrary encrypted state. And this honest majority trust that we have for those clusters is further being reduced by us, for one, allowing those individual nodes to remain anonymous. So the cluster itself, a node in the cluster doesn't know its peers, so the communication happens through relayers. And on top of that, we have a protocol in place that automatically allows to select nodes based on distributing parameters, and we have a latency-based geolocation system where we essentially enforce that nodes are not part of the same data center to further reduce risk of compromise and increased resilience. And so in closing, what we are building is a trustless architecture. And of course, there's remaining trust involved, but this remaining trust is the lowest trust that you can have in such a system. It's not anymore, I have a large supply chain, I have a lot of trusted actors, and if there's one point in the supply chain, everything can get compromised. In our case, it's the exact opposite. As long as there's one that isn't compromised, you have safety. We have verifiability, so the outputs of our computations are so-called publicly auditable, which means that the recipient of the output, the computation customer, can verify that the computation output is correct. They don't have to trust that they've performed the computation correctly. We are significantly more performant than other cryptographic approaches towards confidential computing, and with our collateral and cheating identification mechanism, we can enforce guaranteed execution across this network. And so we offer permissionless clusters to be used in those computation environments, and at the same time also have support for permissioned clusters. So entities that want even lower trust assumptions than this lowest trust assumption, they can run their own hardware and have other people also run their own hardware, and then they are able to just do data collaboration over those distributed data sets. So what I want you to take away from this talk essentially is that Trusted execution, of course, is not dead, but trusted execution is flawed, and for cases where highly sensitive data is processed, a more cryptography-based approach can make sense, and both systems can symbiotically work together. Yeah. So if you're interested in what we're doing, you can visit arcium.com, and we are right now in the process of moving into our first live test network. Thank you.
We have a couple minutes for questions. If anybody wants to raise their hand, I've got a mic here.
Hi, great talk. I had questions on the details of the MPC protocol. So suppose you have, say, a client has some input to a machine learning model, and some company owns the machine learning model. Typically, the way I imagine is they run the joint computation together, right? So is that how it would work, or?
I mean, it could be, but it actually doesn't have to. So both parties could just select, or essentially just the company owning the machine learning model can create such an environment with a cluster associated, and then have a public RPC interface where you can infer that model, for example, and then it's just triggering a computation inside of that environment.
So the client wouldn't participate in the MPC protocol
No.
make a cluster?
Yeah, exactly. That's important, that the end client doesn't have to do that. It's of course always possible, but only really makes sense for the cases where we have the most sensitive data, right? Where you don't even want to trust that in this cluster with a good track record, there's one honest participant. In those cases, it makes sense, but otherwise, you would just use those existing nodes as a cluster. Yeah.
So all the parties participating in the MPC protocol are owned by Arcium?
No. It's a open network. So we have basically all of the node operators, Coinbase, and all of those that do node operation services for the existing blockchains. They also do that for us, and we have some TEE operators as well. So we also support running a node with a TEE, and so we are globally distributed. We have those nodes globally accessible, and anyone can essentially become such a node operator. There's a KYB process where you prove your identity essentially, but yeah, it's an open network. So Arcium itself is not involved in this process at all. We are essentially a non-profit foundation, if you will, that develops this open source software. So it's fully open.
Okay, thank you.
I think we got time for one more. Maybe two more.
Thank you for the great talk. At the beginning, I think you mentioned something about that the flaws, one of the flaws in TE was that it's performance issues or performance overheads.
Yeah.
And towards the end, I think you were talking about that this is more performant than other cryptographic approaches.
Yeah.
But could you comment on how does this compare
Yes.
with?
Yeah. So that really depends on the algorithm that you're executing. So there's since for those multi-party computations, what you need to do is, or what we are doing with the software we are offering is, you have to compile your normal computation that uses some instruction set into an arithmetic circuit. And an arithmetic circuit has two base operations, which is addition and multiplication, not of binary values, but instead of field values, or in our case, elliptic curve points. So it's a different representation of computations. And so additions in this computational representation happen locally on any machine in this network, but multiplications require network communication. And so that's essentially how is the algorithm exactly structured that then determines the performance. But so what we've seen in testing so far in the first protocol that we used was slow down in the range of 10x. But we are able to improve on that by using so-called packed secret sharing, which allows us to further reduce the communication rounds required for multiplication, so we can batch that together.
All right, I think we're out of time. Let's thank Yannik for a great talk.